Okay, in the last lecture we talked about the gravitational field and how it gets weaker as we move further away. Um, and so now we need to extend that into the idea of gravitational potential energy. So here we are close to the surface of the planet. Okay, close to the ground here, the brown ground. Okay, and we have an object, and the way we've defined our potential energy so far is that if we have an object that's suspended over the surface of the planet, okay, by height y, and it's got a force acting in that direction, we have a potential energy due to gravity. The gravitational potential energy on this object is going to be the force of the gravity, the mg, times the y, which is the height that it's suspended above the ground. Okay, and our object moves down, and since the object moves down, it is gaining kinetic energy, which means that gravity, this force, does positive work. Okay, but if this moves down, that means it would be a decrease in the potential energy. So the work done by the conservative force that is gravity, if you remember, is equal to the negative change in our potential. Okay, or another way to write this is that that our change in potential, okay, is equal to the negative integral of the conservative force times times the ds, or times the distance that over which it's exerting the force. Well, let's imagine now that we have our pale blue dot in space, and here is our. In fact, I learned my lesson from the previous lecture that I'm actually going to draw a perfect circle. Okay, and this is the Earth. Now imagine we're going to launch a rocket. Okay, and as we launch a rocket, in fact, this is how we actually do this. Is that we launch this rocket vertically upwards, and then it tilts over, and then it reaches someplace out in orbit. Out here. Okay. Well, because the work and energy is non-path dependent, it is path independent, our delta U, our change in our potential, is equal to the integral from our initial radius, our initial distance from the center of the Earth, which is this. This is r I, to r f. That should be a negative out here. Okay, and what is the force that's acting? Well, the conservative force is gravity, so that's going to be g big M little m over r squared. Okay, and in the negative r hat direction. Okay, d s. Okay, now here is our s. This is the distance that we traveled, but only the part of the force that actually acts in only the part of ds that is in the direction of the force actually contributes to our, I'm sorry, totally, this should be delta U equals all that. Only the part of ds that actually travels in the direction of the force accounts for, it gets to count into the work. And so that's only our change in our radius as we move further away. So this really gets written, so our ds changes to dr. All right, and so our delta U equals equals negative g all right, yeah, g m big M little m integral of our initial to our final 1 over r squared dr. Okay, well, we can rewrite this, and this becomes Okay. Oh, there it is. Okay. This negative actually canceled that negative, so that goes away. That's what I was missing. I was confused on my negative. So the negative in there for the r hat cancels that negative, so it becomes, that makes this a positive. We don't have to worry about that. So this becomes gm, big M, little m, integral from r initial to r final of r to the minus 2 dr. And we continue to integrate this, and all of a sudden this becomes okay, so the derivative of something is going to give us r to the negative 2, so it's r to the negative 1 over negative 1. So that's going to be g big M little m integral. I'm sorry, not integral anymore. This is r to the minus 1, negative r to the minus 1, as we go from r initial to r final. Let's be tedious here and let's plug these in. So we're going to go equals g big M little m negative 1 over r final minus negative 1 over r initial. Close those parentheses, and this becomes a positive in here, and this is a negative, so we're actually going to switch this around, and our delta u is actually equal to g big M little m over r initial minus g big M little m over r final. Okay, or in other words, it is the potential, it's the initial potential energy. Oh, I lost you off the screen, didn't I? Oh, I did. I way off the screen. It's one of the hazards of doing this on my own. In other words, the initial potential energy, or change in potential, is equal to its initial potential energy minus its final potential energy. So it's because it's negative of the work, and so the work would be the work done by gravity would be final minus initial, and so the potential is the initial minus the final. Okay, so with this idea, what would be a good place to choose? Okay, where is a good place to choose our initial potential energy equaling 0? Because we can have it arbitrary, and it can be wherever we want it. Right? So, for example, when we are dealing with potential energy near the surface of the Earth, we choose the ground as 0 potential because it's easier it's a lot of times easier to do the math because we measure things from the height of the ground. Well, do we want to do it at radius equals 0? Well, because that's sort of where we would be if we did, if we're talking about the ground, except the place where, where your potential energy equals 0 would be right here. Well, what happens to your potential if we take 0 to be there? Well, we have our potentials to be, one of these becomes 0, and we start dividing by 0, and that's a cosmic no-no. You can't do that. That's that's chaos. Cats and dogs living together. That doesn't work. So we're going to choose a different place. Okay, because we cannot divide by 0, we're going to choose a different place. We're going to choose a better place. We have a better place to decide where potential energy equals 0. Okay, and we're going to set U equals 0 at R equals infinity. What? Well, think about that. If we let R, let R approach infinity, R initial approach infinity, then the potential energy at Ri does equal 0. Okay, so let's take a look at our equation again. If we take our initial potential energy, if we take this to be infinity, this entire term, or as this approaches infinity, this entire term becomes 0. And so our delta U equals our negative work again. All right, so let's work that out here. So we have UF, our change in potential is U final minus U initial. Okay, and that equals, from our previous page, G big M little m over R initial minus G big M little m over R final. And if we said that our U at our initial place equals 0, because this is infinity, this equals 0, then what we are left with is that our force of gravity, or the potential energy due to gravity, is equal to big G, big M little m, over R. And this means that all potential energy due to gravity is negative. But that's okay, because we don't use the absolute potential energy, okay, of an object. That's not the necessary part. What is necessary is the change. We don't worry about UG. We worry about delta UG, and this is where we get our energy changes. And you can always find a positive change in two negative numbers. If something goes from, negative 35 joules, okay, and it changes its position so that it now has a negative 20 joules of potential energy, this is an increase of 15 joules. Okay, this is what delta U equals. Okay, here would be an increase in potential energy, and it would be negative work done. It would be work done against gravity to increase its potential by 15 joules. Okay, so if we have an object I'm sure I'm getting this right. All right, so let's say we have an object out in space that is under the potential energy. So here's our mass right here, and there is a massive object over here, and a massive object over here, and a massive object over here. Okay. The potential energy on, there's number 2. The potential energy on this guy, okay, the U on this guy is going to equal G times the mass of 1 times his mass, and then we'll call this as a little mass, over R1 at negative, plus negative G times the mass of 2 times the little mass over distance to 2, plus negative G M3M over R cubed. Okay, and all these are equal to. Now, when you get into assume you will be, if you guys are taking this class, and the chances are you going into engineering or some other hardcore, you will be taking a harder physics class with some more advanced math, and the force, you will find that the force that acts on this object is equal to the negative gradient of U, and this comes out really nice because it essentially is a partial differential equation. It's a set of partial differential equations that isolates the component from each particular mass. And we're not going to go into that, although if you take Math 6, I believe it is, at Fresno State, if you're doing that right now, then you'll start getting into gradients. But that is it for gravitational potential energy, and we'll see you guys next time.